Thank you very much, Alan, for inviting me here and give me opportunity to talk about this issue here. So I'm going to talk about suspension point interferometers today. But before starting my talk, I'd like to mention that this talk was prepared by the help of those people. And so, as an introduction, so suspension point interferometer, and I call it SPI for short from now on. It's an active vibration isolation scheme using auxiliary laser interferometers as sensors. And there are actually, is there a pointing stick? Thank you. So there are several advantages to it. And I'm not going into detail later, so I'm going to skip this, but there are several advantages. So I tested this technique with prototype type experiment and got basically 40 dBs of noise suppression at low frequencies. And in this talk, I'm going to also talk about the application of this technique to advanced LIGO and LCZT and also LISA, actually. So to start with, the seismic noise is, as most of you know, it's a dominant noise source in the ground-based gravitational detectors at low frequencies. And it has various impacts on the interferometer. And in terms of duty cycle, of course, if we have a large seismic excitation at low frequencies, we lose the stability of interferometer, so we lose the duty cycle. And also, once if you unlock the interferometer and you want to relock the interferometer, if the seismic disturbance is too much, then it's difficult to lock the interferometer again. So it takes time, so you have long downtime. So that's going to also increase the downtime and decrease the duty cycle. And on the other hand, in terms of sensitivity of interferometer, of course, the low frequency seismic noise directly limit the noise level of interferometer at low frequency. We get so-called seismic wall at low frequency. That's for sure. And in addition to that, so the low frequency noises can increase the higher frequency noises coupled with low frequency motion of the mirrors. For example, if we have a large motion at low frequency, coupled with nonlinearity of detection system like photodetector, we get up conversion noise. That is one way to create high frequency noise from low frequency noise. And also, if we have a large horizontal motion at low frequency, then we have to keep the mirrors in place by pushing it horizontally. But a horizontal actuator is not perfect. So if we have some horizontal to pitch coupling, and that is, according to Rana, it's a kind of dominant source of creating pitch motion in current LIGO. And we want to reduce it. And also, we can have a contrast defect by moving mirrors so much at low frequency. That will increase the sharp noise or coupling of laser noises like frequency noise and intensity noise to the output of an interferometer. And also, the actuator noise is basically, we have to have sufficiently strong actuators on the mirror to keep that mirror from moving and to stop it against seismic disturbances. So if we have larger seismic noise, then we have to use a stronger actuator. But that means, in turn, you can more likely to introduce at higher frequencies the noise coming from actuator, like a coil drivers or whatever. So those things, so through those various passes, the sensitivity of the interferometer is impacted by the seismic noise. And for those reasons, we want to reduce the low frequency seismic noise. And here comes the suspension point interferometer idea, which was originally proposed by Professor River here. I think he's there. And in 1987, it's 10 years ago. Wow. And then, so 20 years, yeah, 20 years ago, yeah. And so this is a conceptual schematic of the system. Well, there are various configurations possible, but this is one example. So it looks like two interferometers suspended in chain. And the lower interferometer is, I call it the main interferometer, or MIF. And that interferometer is used for, of course, in gravitational wave detection. And the upper interferometer is called the suspension point interferometer. And we use it for active vibration isolation. And how are we going to do this? I'm going to explain it using the Fermi pair arm here. So this is a zoom up of the Fermi pair arm. So the Fermi pair interferometer measures basically the distance between two mirrors. So and if we lock the upper interferometer by Pound-Weber-Hall method, for example, and then we basically lock the two mirrors, the distance between two mirrors rigidly. So we can virtually consider this stage as a virtual rigid bar. And then if there is a differential seismic excitation at the top, then because this is a rigid bar, it won't transmit this vibration to the lower stage. So this stage stays quiet. No, in principle, no seismic motion here. Seismic noise here.
This call has been terminated. Please contact the moderator if there.
Okay. And if we have a common motion of the top stage like this, then this rigid bar, of course, follows this motion. But if we have identical pendulums here, then these pendulums make exactly the same motion. So the distance between them is, again, not changed. So we don't see any seismic noise at this stage, in this case too. But this is only true if the assumption of identical pendulums is true. So what happens if there is a symmetry here? And the next slide is a little bit busy, but here I'm trying to kind of quantify the amount of this asymmetry, the impact of this asymmetry to the performance of the suspension point interferometer. So if we call this transfer function from this stage to the final mirror, and this pendulum is H1 and the other one is called H2. And then I make this so-called common mode rejection ratio for suspension point interferometer like this. And this is basically a conversion coefficient from the common motion of this suspension point interferometer stage to the differential motion at the end of the stage. And if you plot the CMRR as a function of frequency in the case of single pendulum, then you can write like this. And the common CMRR is the amount of leakage from common motion to the differential motion. So if it is smaller, it's better. Okay. So at lower frequencies, this common mode rejection gets better and better as the frequency goes down. It's 0.1 hertz and it's 100 hertz. And we have a peak at the resonant frequency of those pendulums. And then we have some saturation in CMRR. And that saturation is basically proportional to, in this case, the difference of the resonant frequencies of those two pendulums. And I put about 1% asymmetry between those two of them. And then you get 10 to the minus 2 CMRR at higher frequency. So the symmetry of those two pendulums is, or whatever suspension chain hang from the suspension interferometer stage is very important and crucial to get better, good performance with this SPI. And there are also other factors which limit the performance of suspension point interferometer. And the most significant thing is this cross-coupling from other degrees of freedom, like vertical motion or pitch or your rotational motion, because suspension point interferometer is always sensitive to horizontal motion. So you can't really sense and cancel the vertical motion, pitch, and yaw. Actually, you can sense pitch and yaw motion by using waveform sensor. And yeah, that's one possibility. But vertical motion is very difficult to detect with suspension point interferometer. So if those couplings are overwhelming to the horizontal motion, then this is going to be the limit. And also, if you have, because you have finite gain for suspension point interferometer, this is the absolute limit for the performance of maximum amount of suppression you can get. But usually this is not going to be the limit. This guy is more significant. And of course, if you have noisy suspension point interferometer, you will suffer from it. But neither of those that significant in reality. And then let me compare the suspension point interferometer with other conventional ways of vibration isolation. So many of you know that the most standard way of vibration isolation is passive vibration isolation using harmonic oscillators like pendulum. And in this case, you have a very good isolation above the resonant frequency of this pendulum, but at lower frequencies than the resonant frequency, you don't get any attenuation. And also at the resonant frequency of the pendulum, if you don't have a good damping, then you can easily amplify the vibration, and which can cause some instability problem in the interferometer. So that is the passive vibration isolation. And in the active vibration isolation, well, that could mean many things, and it includes the suspension point interferometer. But in this case, in general, it measures the ground motion by sensors and cancels this vibration by feeding back to some actuator. It's a very simple idea. And why do we use the sensor for active vibration isolation system? Is accelerometers. And it has, again, no DC sensitivity because it's measuring the acceleration. So actually, the common property of those two schemes is that so our objective is to isolate the mirror from the vibration. And when we talk about this, we want to stop the mirror. And if we say, I want to stop a mirror, then you have to specify with respect to what you have to stop it. And so you need a reference frame. And in those two cases, we're stopping the mirrors with respect to the local inertial frame of the mirror, right? But in contrast to this fact, SPI is measuring the same degrees of freedom as the main interferometer. So that's why you call it a global sensor. And so the reference frame here is the relative distance between the mirrors, not the local inertial frame. So for that reason, we can use the displacement sensor, not accelerometers. So the displacement sensor, of course, has DC sensitivity. That means we can have DC vibration isolation performance. So we can have good vibration isolation performance at very low frequencies. And also another good thing about SPI is because the SPI sensor is basically the interferometer, it could be potentially as good as the main interferometer. So the noise, we can achieve very low noise. So in some cases, the noise from the accelerometers can limit the performance of active vibration isolation system. But in the case of the suspension point interferometer, if you make a very poor interferometer, yes, you can be limited by noises. But in many cases, you don't have to worry about the noise. That's another good thing. Now, so let me summarize the advantages of suspension point interferometer. So the characteristic is it's low noise, and it is a displacement sensor. So we can get ultra low frequency vibration isolation. And so from those characteristics, we can get by reducing the seismic noise at observation band, we can basically expand our observation band further down to the low frequencies. And also by reducing the RMS motion of the mirrors, we can stabilize the interferometer, or we can achieve robust lock acquisition, which is gonna improve the duty cycle. And also we can reduce those technical noises like razor noise, actuator noise, and conversion noises, as I discussed before. So these are the benefits of the suspension point interferometer. And now, to confirm this scheme, to confirm that it works in reality, I made a small prototype experiment, which is a 1.5 meter long fabric interferometers, looks like this, and suspended by 2 pendulums. and using the triangular small mode cleaner for frequency stabilization. So basically, I have a laser, the light coming out here, and this is a mode cleaner. This is about 20 centimeters long rigid cavity, and the laser frequency is locked to this mode cleaner, so that it is stabilized. And I also have, although it's not shown here, I have intensity stabilization loop for the laser. And then after the mode cleaner, the beam is divided into two beams and injected to the suspension point interferometer and the main interferometer here. And basically, I want to measure the noise of the interferometer and compare it when the suspension point interferometer is not used and when it is used. That's the whole idea of the experiment. And this is a kind of whole setup. This is a laser and mode cleaner chamber, and these are the kind of complicated suspension systems. And this is a laser bench, and I use a 1064 very standard CaJAGWR laser. And this is a mode cleaner. I used it's made of the spacer is made of superinvert to reduce the thermal expansion. And so yeah, and it's locked to the laser using standard foundry over hole method using 40 megahertz frequency. Yeah.
Seismic stack, I guess, but is it vacuum?
It is in vacuum chamber. Yes, everything is in.
So you operated all that stuff in vacuum?
Yes, it's yeah. So yeah, I put photo detectors in vacuum and everything, and it works fine. It works fine. Yeah, it's yeah, peak motors. Yeah, I also have the vacuum-proof versions, but this is just normal peak motor, but they work fine. So yeah, well, I'm not sure in the long-term, stability of those, but for my experiment.
The degree to which it may have degraded your vacuum?
Well, yeah, the vacuum, degree of vacuum was not that good in this.
What is your power level?
I mean the laser. Laser is it's 5 milliwatt, rated to 5 milliwatt, but I think it's a 200 milliwatt or something like that. Yeah, at that point. Yeah. So basically, yeah, this is a mode cleaner chamber, and then this is a drawing of the suspension system. It's basically triple pendulum suspension with two M-gas filters, which I will explain a bit more in detail in 2 slides later. But so the first stage has eddy current damping by putting magnets in here, and this is the suspension point interferometer stage, and this is a final stage which was surrounded by recoil mass, and it's actuated from the recoil mass. Right. And then, so yeah, this is a photograph of the system. And then one of the key components of the suspension system is M-gas filter. So it's M-gas is monolithic geometric anti-spring. It's a very low frequency vertical spring. And the reason why I use this is because if you have large vertical motion, then you are overwhelmed by the coupling from vertical to horizontal. So then your noise is limited by vertical vibration, vertical seismic noise, and you're not going to see the improvement of seismic reduction of seismic noise by the suspension point interferometer. So that's why I needed a very good vertical vibration isolation. And so basic idea of this spring is you have a positive spring from the elastic force of the deformation of the material, and from the backwing effect of the spring, you get a negative spring. And by canceling out those two spring constants carefully, you can get extremely small spring constant. And the resonant frequency I got was less than 0.2 Hz with 40 centimeter diameter spring. And so I used this system, two of those filters for one suspension. But actually, because this one is very sensitive to the temperature change, because the elastic constant change by the temperature, and then this balance is changed, then you have large drift by the temperature change. So I had to compensate this temperature drift to keep the interferometer running. So how I did it was, this is a zoom up of the first stage, a damping stage. And if you remove the outer shell, these are the magnets used for eddy current damping. And if you look at here, zoom into this stage and makes part of it transparent, then we have I have photosensors here, which monitors the height of tip of this M-gas filter. And this signal is feedback to the horizontal actuator so that it keeps the height of the M-gas filter at constant level. So in that way, I can compensate the temperature drift.
This is the second stage, right? Compensate on the second stage when I close the
Mm-hmm. Okay. Yeah. So I have to do both stages.
Oh, both.
Yes. Yeah. Actually. Yeah. Yeah. That was the sensor for the second stage, and I have another sensor for the top stage. Yeah. Yeah. And so I have basically 8 control loops for this interferometer. So the first two is the frequency and intensity stabilization for the laser, and then I have 4 loops for the temperature compensation of the M-gas filters, and then finally I have 2 loops of pound river hole loop for suspension point interferometer and the main interferometer. And here I'm going to show you some results.
Same finesse in both interferometers?
Yes, I used the same one, but the reason was that I just bought mirrors in batch. I could use smaller finesse for suspension point interferometer.
So to realize that the power of the suspension point interferometer for helping in lock acquisition, you lower finesse.
Yes. For this purpose, yes, we have to use low finesse. But for this experiment, it was not required, so I just used the same mirrors.
What were the
500. Yeah, not that high. Well, yeah, but it's only 1.5 meters. So. Okay, and anyway, so this is basically the noise spectrum of main interferometer from 0.1 Hz to 50 Hz. And the lower plot here is a cumulative RMS iterated from high frequency to the low frequencies of this spectrum. And when I turn on the suspension point interferometer, the noise goes down like this. Well, it has a very large span, so it doesn't look like a huge suppression, but it is actually a factor of 100 suppression here, 40 dB suppression here. And let me explain some peaks which you might be interested in. So these peaks are pitch resonance of the suspension point curve. Yeah. Well, actually both pitch resonances. So yeah, there are some peaks seen, and these are other not well identified mechanical peaks in the suspension system. And I believe that here we are limited by the laser frequency noise around this point. And this peak here sticks out of the blue curve is the pendulum resonance of the last stage hanging from the suspension point interferometer. And once you lock the suspension point interferometer, you basically isolated the final stage from the upper stage. That's the whole idea of reducing the sound noise. You isolate it from the above. So in that way, we lose the damping by the first stage. We have eddy current damping at first stage, but the final stage is isolated from the above. So that's why you get a higher peak, a high quality factor peak. But actually, in terms of the stability of the interferometer, this peak is not that serious problem because, okay, you have a very high Q pendulum, but that means your actuator also has a peak at exactly the same frequency. So at this frequency, even though the motion is larger, we can easily suppress this motion. So that's the reason I'm not that worried about this. Okay, and if you look at the RMS of this here, I think I have something to say. No, okay, sorry. Here. The RMS, total RMS was reduced by a factor of 9 compared to when the suspension point interferometer is not used. So it's a reduction we get. And if you convert that spectrum into the speed and it takes RMS again, then the RMS speed was reduced by the factor of 7. And the relative speed of the mirrors is very important for lock acquisition. If the speed is smaller, then it's easier to stop it, obviously. So for this reason, I just calculated speed spectrum, and so we get a factor of 7 reduction.
What's the indicated frequency of the
Okay, it's 1 kilohertz. Yeah, for both interferometers. Yeah, it's 1 kilohertz. So the gain of the suspension point interferometer is very high. Yeah. Yeah, sure. No.
It's the gravitational waves. I mean, if the gravitational wave goes by, it's going to make a signal in both.
Yes.
Depending upon how you choose the your gain and your sensitivity, you might have to read it out from both.
Well, I don't really think so. Well, because so if you suppose that the frequency of the gravitational wave is higher than the resonant frequency of this pendulum from suspension point interferometer to the main interferometer. In that case, those two interferometers are kind of isolated by this pendulum. So if the gravitational wave try to shrink the arm, then yeah, the main interferometer is shrunken, and then the suspension point interferometer is also shrunken. And then the SPI control loops try to expand it so that you might worry about this expanding might cancel out this shrunk. But this motion at the suspension point interferometer stage is attenuated by this transfer function of pendulum. And then in this case, the resonant frequency of this pendulum is like less than 1 hertz. So at 10 hertz, the attenuation is more than a factor of 100. So maybe you will lose 1% of the signal strength, but not that much. So that's the way it works. So at the observation band, I don't think you have to worry about this cancellation. Yeah. Okay. Right. So and then I also measure the transfer function to check the performance of the suspension point interferometer. So what I did was I have a horizontal actuator, which is a coil magnet actuator on this stage. So I excited this stage horizontally and measured the transfer function to this stage, and measured in the both case when the suspension point interferometer is on and off. And this blue curve shows that the measured transfer function when the SPI was off, and the red curve is again when the SPI was on. And the reduction here is actually more than 40 dB. It's almost like 60 dB here. And those dashed lines are the model calculation by point mass model, very simple model. And assuming 0.225% asymmetry in the length of the final stage pendulum. And you can see that a huge discrepancy here, and this is a resonance of M-gas filter. So I do believe that here we are limited by the vertical motion because our excitation is not purely horizontal. So we have also some vertical motion excited here, and that comes into play here. But and also here and here we see some couplings from pitch motion. So those couplings from other degrees of freedom is what you have to fight against when you do the suspension point interferometer. But still, we get a very nice, like almost 40 dB suppression up to this frequency. So this is a result we get. And after this, let me talk a little bit about the possibility of using suspension-bound interferometers in advanced LIGO. So there's some discussion in people like between Rana and other people about using suspension point interferometer in advanced LIGO in addition to the current, current seismic attenuation chain, because the primary motivation was rock acquisition. So here you see there's some estimate made by Rana about seismic motion at the BSC chamber, and this rule curve is SE requirement, but he estimated when the seismic motion is noisy, it can go like this, the red curve. So in this case, RMS speed of mirror could be 1 micron per second in noisy time. And according to the estimate and simulation by Osam Miyakawa, so at least the mirror speed, relative mirror speed must be less than 25 nanometer per second to log the interferometer. And in advanced LIGO, we have to log the arm cavity at the first fringe. That means, okay, you would log the central part of the interferometer, and then you want to log the 5-pair arm, and as the mirrors move, it happens to cross the resonance point, and you want to catch and stop the interferometer, stop the mirror at this moment, at the first fringe. Otherwise, when the mirror passes through the fringe, then the condition in the central part locking is destroyed, and you screwed up everything, and you have to redo it from the scratch. So, so he estimated the portion of time when the mirror's relative speed is less than 25 nanometers per second, and there are several schemes to log the interferometer, but please look at this. So if you don't use suspension point interferometer, then we get only like 10% of time satisfying this requirement during the daytime. And he used some, I think he used my result of reduction of factor of 7 by this speed. And in this case, we can get up to 56% of the time we can log the interferometer. And so these are the primary motivation for advanced LIGO suspension point interferometer. But in addition to this, of course, we can gain other benefits from suspension point interferometer, like improved stability and duty cycle during the science mode operation. We can use suspension point interferometer, and of course, it reduces optical conversion noise and pitch motion, contrast defect, or other technical noises. So these are the reasons we want to do advanced LIGO suspension point interferometer. And now the configuration of the advanced LIGO suspension point interferometer is considered by me and Bram Slagman and Anu and Matt Evans. And then we found that the penultimate mass in current design is not exposed to the beam tube. So we can't use this stage without modifying the quartz suspension or design. So we decided to use this seismic platform, ISI, and for the suspension point interferometer, and hang the mirror down to the beam tube height. But we can't use this kind of rigid mount because we get tilt in ISI, and this tilt is converted to a huge horizontal motion by this long leverage arm. So we have to decouple this tilt. And Matt Evans' idea was to use long pendulum to hang the SPI mirrors and feed back the force to ISI. This was, and he has written simulation code for this configuration. So I'm going to show you this estimate of the performance of advanced LIGO SPI by using this configuration. And also, this is just an idea by me. Maybe we could hang a periscope like this to make this. And if we make the center, if we concentrate the mass around here so that the center of mass of this periscope is around here, then in principle, we don't get a tilt problem. But it's just a rough idea, so it needs more critical examination. And so let me show you this is a kind of schematic drawing of long pendulum advanced LIGO SPI by density point. So here we have main mirror, and we hang this SPI mirror from here, and have some actuators here, all sensors to monitor the motion of the SPI mirror. It looks like this. And then this is a result of simulation. And so we used a single pendulum suspended from ISI and Farber Michelson. In this case, it's not Michelson, but we included beam splitters so that the SPI configuration is Farber Michelson with arm fitness of 10, and input power is only 1 milliwatt. And the signal is fed back to ISI stage with a unity gain of 8 Hertz. Okay, so it's a bit busy plot, but basically, please compare this gray curve. It's a total noise without SPI, and this red curve, which is the total noise with SPI. So there is a huge reduction up to like 0.8 Hertz. And these are the breakdown of the noise sources. But basically, please look at the RMS. Without SPI is something like this, and with SPI, the RMS, the green dashed line is something like this. So the total RMS displacement was 0.15 micrometer without SPI, and with SPI it goes down like 0.7 nanometer. So it's more than a factor of 200 reduction in the displacement noise. And if you convert it into the speed noise, basically the total RMS was reduced from 0.2 micrometer per second without SPI to 2.1 nanometer per second. So the requirement was 25 nanometer per second. So it's well below it. But actually, I noticed that this number here is less than factor of 5 less than 1 micrometer prediction in the noisy time. So I think the injected noise estimation was not a noisy time one. So in the noisy time, we expect the total RMS to be factor of 5 larger. But with factor of 5 amplification here, still it's below this 25 nanometer per second. So we think, we can achieve reasonable performance with this configuration. And if you want to know more about this, here is an advanced LIGO wiki page, and also I have some LIGO DCC document on this. Okay, and how many minutes I do? Okay, so in the rest of this talk, I'm gonna basically show you the work in other people. And this one is the very interesting work done in being conducted in ANU. It's a relatively new idea called pseudo-random noise heterodyne interferometry or lock acquisition interferometer. So basically, they are working. There are the ANU people also interested in a suspension point interferometer. So I think they're actually responsible for advanced LIGO SPI. And so me and Matt is working in cooperation with them. And basically, why considering about SPI, Daniel Shadok at JPL, I guess, he came up with this new idea of pseudo-random noise called heterodyne interferometry to monitor the motion of mirrors independently with rather dynamic range. So they are proposing to use this interferometer for the lock acquisition of advanced LIGO. And if it works, I think it's going to be a kind of paradigm change of the lock acquisition scheme. So let me quickly explain you how it works. So basically, it's a heterodyne interferometer. So basic idea of heterodyne interferometry is if you want to measure the light path difference between this red path and green path, then you shift the first you divide the laser, and then you shift the frequency of one beam by some modulation, and measure the beat between two signals. And by measuring the phase of the beat, you can see the path length difference. But in this case, I think I should have done it. Yeah. But if you have multiple optical components, and if you want to measure the reflections from those mirrors independently, if you do the standard heterodyne interferometry, your demodulated heterodyne signal contains a mixture of all the motion information from those mirrors, and you can't independently extract the information. But the trick here is, for one beam, we apply a kind of random phase flip, phase 0 or phase pi. We're using EOM. So when you see the beat signal here, it looks like this, because this is a because your heterodyne signal, normal sinusoidal signal, is flipped by some points. So you get this kind of noisy signal. But if you know, because you know how you flip this phase, you can revert it by demodulating it at this stage. So you can just invert this signal here, and no inversion, and inversion here, and something like, to recover the original heterodyne signal. But you have to use proper delay time to apply this PRN demodulation from here. And that delay time depends on the distance from the mirror to the photodiode. So they are different for different mirrors. So if you use the time delay for this mirror and try to reconstruct the heterodyne signal, then basically the signal you get is mostly the motion of this mirror, and the motion effects from those other mirrors are kind of spread out in the frequency spectrum. It's a frequency spread communication, something like that. It's analogy to those techniques when you use in a cell phone and many communications applications. So with this technique, you can measure the motion of those mirrors in the same light path independently. And because it's a heterodyne interferometry, it depends on the heterodyne frequency, but you have a very large, like maybe meters of dynamic range. So, and okay, I think I should go. So, and here it looks like just Fabry-Perot cavity. So you can basically measure the relative distance between those two mirrors, and like pound-river hole method, you can lock the Fabry-Perot cavity. But here you have huge dynamic range. And then, so the basic idea is before locking the interferometer, you monitor the motion of each mirror with this secondary interferometer, PRN interferometer, and bring that mirrors close to the resonance condition, actually at the right position. And then once you have resonance, then you switch your control signal over to pound-river hole signal, or whatever signal you use for science mode. That is the idea here.
How do you know where the resonance condition is?
Well, you just sweep it. First you lock it and apply some offset and sweep it, and when the right is building up in the cavity, okay, this is the resonance condition.
And you'd expect that to be stable, so you know what time, or is it different every time you have to sweep?
I think we have to sweep every time, but yeah, but could be wrong. So yeah, but I think we have to do that. And then, so that's the whole idea. And actually, if you think about the configuration, you can also monitor the positions of beam splitter and also not the beam splitter, but also signal recycling mirror and recycling mirror and everything. So you have kind of God's eye, if this thing works, you know before locking the interferometer, you know the full information where those mirrors are, and you can just move it and as you like, and bring them to the proper positions and switch over the interferometer. And so, but the question is the noise and the precision of this method. Surely this interferometer is less sensitive than the main interferometer. So in order to estimate or evaluate this scheme, they set up a small fiber cavity, and they locked this cavity by the found-over-hole method. And then they injected their pseudo-random noise coded laser to measure the relative motion here. And so assuming that the pure PDH blocking is very stable, they want to measure the noise of their method. And the result is, this is the time domain signal of each mirror's motion, and this red curve is the relative motion. And this is the frequency spectrum of the noise. And so, yeah, it's like 3 times 10 to the minus, 300 picometers above 1 hertz. And they suspect that this is the noise of found-over-hole scheme. So, I just think that probably this is a laser noise. I don't know. But anyway, so they get some very nice sensitivity, and they are trying to improve it. So I think, at least at this moment, this scheme is very promising, and we could use this also for the log acquisition of the interferometer. Right, and then let me move on to the LCZT and suspension point interferometer. So this is a schematic, the drawing of LCZT suspension system. It's like a Virgo supernator system, and it's basically the Ricardo's SAS system, actually. And we have suspension point interferometer. I think it's a kind of misleading. We have several beam tubes, but I think we use one beam tube. Maybe the drawing is a bit old.
The last beam tube starts later on for carbon reasons.
No.
It becomes a single pipe.
Yeah.
I asked the question so that it becomes a pipe later on.
Yeah, it's a single pipe. Anyway, so here is the suspension point interferometer, and then why we want to use it is, of course, we have the same reason as the advanced LIGO, but we have more serious problem here because the LCZT is a cryogenic interferometer, so we have to cool down the mirrors. And in order to cool down the mirror, we have to connect so-called heat link wires to the penultimate mass to suck out heat from the mirrors. But these heat link wires are connected to cryogenic shield, and it has some vibration. So although we have very nice filters out there, there is a shortcut path here. So we have the extra vibrations introduced, so we have to reduce it. And so the idea is to put a suspension point interferometer here and basically monitor the motion introduced by the heat link and suppress it. And the reason why we need suspension point interferometer is because this sensor is pretty close to the main mirror, so it has to be very low noise. If you have a large noise here, then that noise is also introduced to the main interferometer, and the sensitivity is going to be screwed up. So that's the reason why we're going to use SPI. And there's some rough calculation, but the suppression of heat link noise. So the blue curve is a heat link noise introduced, and without suspension point interferometer, and we can reduce it by a factor of 100 or something like that. So that here the heat link noise is more than factor of 10 above our design sensitivity, but we can reduce it down here. So that's
Does this model include the algorithms of freedom as well?
this No, I don't think so.
Technical horizontal couplings included though.
Yeah, the horizontal couplings included. Yes, that's true. But yeah, I have to ask him. But no, yeah, probably. Yeah, I have to check it. To answer it. Yeah. Now and then finally, this is view. I'm going to show you 3 view graphs from Kenji Numata at Goda's specified center, who is working on the suspension point interferometer or suspension platform interferometer, whatever, in Goddard for the test of LISA components. So basically, to test the LISA interferometer components and so on, they need a very stable environment. And to do so, basically, he built 2 optical tables, which and the relative motion of those tables are monitored by suspension point interferometers. And then by the feedback, the relative motion between those 2 stages are stabilized for high degrees. And I think he has 3 interferometers, so that not only the horizontal motion, but also he can monitor the pitch and the yaw motion of those 2 stages. And these are the setup. He used so-called hexapod for the actuation of the optical stage in 3 degrees of freedom, I think. Yeah. And so then the result, here is the current result from him. So he achieved a factor of 1,000 reduction at a very low frequency. He's focusing on lower than 1 hertz. And so this is a noise, free running noise. And when he switched the suspension point interferometer, basically he goes down to this blue curve here. And this green curve is LISA goal. So there's something he has to improve, but it's an impressive reduction of the noises. And so the drift is typically before using the suspension point interferometer, the relative drift was 4 microns per day, but now using the suspension point interferometer, it's down to 20 nanometers per day between 2 optical tables. So yes, relatively displacement. Yeah, he has not only a suspension point interferometer, but he has witness interferometer as one to monitor the motion, independent sensor. And these are the output from those witness interferometers. Okay, so that leads me to the conclusion of the talk. So SPI is a low noise and low frequency active vibration isolation scheme, as I discussed, and it can achieve ultra low frequency performance, and we can reduce the RMS motion of the mirrors, which will give us the stable operation, robust localization, and reducing all sorts of technical noises. So we, from initial LIGOS commissioning and also from other large interferometers, we learned that those low frequency noises are kind of headache to us. So hopefully SPI could be an aspirin for those problems. And then by using prototype interferometer, I showed that we can reduce the low frequency seismic noise by a factor of 140 dB at low frequencies, and reduce the RMS by a factor of 9, and the speed was reduced by a factor of 7. And with the transfer function measurement also, I confirmed that SPI can reduce the transmission by a factor of 40 dB up to 20 Hertz. And also there are some people, including me, considering the use of SPI in advanced LIGO and LCDT and for the test of LISA components. And that's it. Thank you very much.